On Sunday, visitors were amazed by a huge plume of steam coming out of a new thermal vent. The steam shot 40 meters into the air. Visitors recorded the moment the steam erupted live at 7:17 a.m. local time, said Michael Poland, scientist in charge of the Yellowstone Volcano Observatory, on Monday Update. Yellowstone National Park is a place of wonder where millions of tourists eagerly flock to see some of America's most beautiful natural sights. Mountains, lakes, valleys, and wildlife galore await tourists visiting this unique and rugged landscape. While many come to see these features and to hit Yellowstone's hiking trails, most people have the park's geothermal landmarks at the top of their bucket lists. The park has geysers, hot springs, mud pots, and fumaroles, all drawing tourists from all corners of the world. These things have in common that they're all connected to a massive magma chamber that boils beneath the ground. In 2025, a groundbreaking paper was published in the journal Nature Communications that brought forward a snapshot of life 2.5 billion years ago, focusing on Yellowstone's geothermal features. While wide-eyed enthusiasts come from far and wide to see the dazzling rainbow colors of the grand prismatic spring or dependable bursts of Old Faithful Geyser exploding into the sky, scientists are interested in different Yellowstone wonders that are off the beaten path. Conch Spring and Octopus Spring. Why are these specific springs so important for researchers? And what could they reveal to us about the origins of life on our planet? Before this study, Yellowstone's Conch Spring and Octopus Spring were relatively little known. Unlike other geothermal features of Yellowstone, these two aren't typically on tourist bucket lists. Located in the lower Geyser Basin, these relatively unknown springs have captured the interest of researchers from Montana State University. What makes them so special to scientists is their opposing oxygen contents. Conch Spring has no detectable oxygen. It's significantly more sulfuric. On the other hand, Octopus Spring is full of oxygen, with 20 micromolar of the chemical element. The researchers, William P. Inskeep, Zachary J. Jay, Luke J. McKay, and Mensur Dilikic, realized that because of this oxygen discrepancy between them, this pair of springs would be the perfect environment to learn about the development of microbial life on Earth. To understand how microbial life first evolved billions of years ago, researchers have turned to the unseen world of microbes thriving in the best of Yellowstone National Park's hot springs. These microbes, called thermophiles, are theorized to have played a crucial role in the development of life on Earth. Around 2.5 billion years ago, the Earth underwent the Great Oxidation Event, often called the GOE. At this time, oxygen levels in the atmosphere spiked within a 200 million year time frame. Why and how does this relate to the springs at Yellowstone? Because of these springs' thermal nature and opposing oxygen levels, scientists from Montana State University have used them as a laboratory. With its lower oxygen content, the Conch Spring has been used to represent pre-GOE Earth, while the Octopus Spring, with its high oxygen content, represents the post-GOE Earth. Among all the incredible animals found at Yellowstone National Park, thermal microbes aren't always at the top of the popularity list. And yet, that was exactly what these scientists were after. What the scientists found was surprising. Both springs had hyperthermophiles, but they weren't equal. As expected, Octopus Spring had a higher diversity of oxygen-hungry microbes, and Conch Spring had a significantly lower diversity. Yet one facet of this data stood out and illuminated important considerations of the pre-GOE Earth. Interestingly, the few hyperthermophiles that did live in Conch Spring had adapted to the low oxygen environment. This means that they are equipped to live in oxygen-depleted conditions. Ultimately, this research provides scientists with a key glimpse into Earth's distant past, and a snapshot of what life could have looked like back then. The hyperthermophiles living over 2 billion years ago would have needed specific genetic adaptations to survive such a harsh environment, just like the hyperthermophiles from Conch Spring. It also shows the vital importance of our atmosphere's oxygen in the origin of microbial life. More oxygen doesn't just mean more microbes. It means more opportunities for other life forms to develop. This key research shows scientists that atmospheric oxygen can make or break the success of life, but also shows that organisms can adapt even to the harshest circumstances.